and a voltage source is also a dynamical system, though it does not move physically, because its quantities, the voltage across the capacitor, the current through the inductor, these things change. So, that is also a dynamical system. In a chemical reaction, you do not see physically anything changing, but there is a chemical reaction taking place. You have mixed hydrochloric acid with sodium hydroxide, then there is a change taking place. Is that a dynamical system? Yes, in the sense that if you dip a sensor of each of the constituents, say sodium hydroxide, then over time the concentration of sodium hydroxide changes, and therefore that is also a dynamical system. So, similarly, you will find that there is dynamical system. Anything in this world can be seen as a dynamical system. Our body is a dynamical system, our heart is a dynamical system, our breathing is a dynamical system. So, everything that we can think of are dynamical systems. And we have found some specific ways of mathematically defining dynamical systems. How are these dynamical systems mathematically defined? In form of differential equations. This much I suppose you have learnt in the mathematics class, right? Why are dynamical systems or dynamics change represented as differential equations? Because in a differential equation you have the dx dt term in the left hand side, and that is defined as function of x. That is the dynamical system. Here this is saying how x is changing with time, and that is then expressed in form of some kind of a function. So, normally we will define a dynamical system like this. Now, if it is a one dimensional system, can you think of a one dimensional system? Not really. Pendulum? No, pendulum is not a one dimensional system. It is actually a two dimensional system, because okay, why? Okay, then in order to test how much you remember, we will today at some stage derive the differential equation for a pendulum, and we will see. But if you write this differential equation like this, there are situations, for example, you have a voltage source, a switch, and then here you have, say, just an inductance. So, this will be a one dimensional dynamical system, but these are very rare. Normally what we do is, given any system, this will give us problem. Given any system, we try to define a set of variables which uniquely define the dynamical status of the system. In case of the pendulum, what can you identify as the variables which uniquely define? Is it the angle? Just if you specify the angle, does it uniquely define? For example, the angle is this much. In addition to that, you have to state theta dot, right? Is it going up? Is it going down? With what velocity is it going up? So, only when that is given, it says, okay, it is in this particular state, right? That is why the pendulum is really a two dimensional system. So, in general, we try to define a few variables in terms of which we will define the complete dynamical status. That means, if these variables are given, x with a value 1, y with a value say 1.5, z with a value of say 3.9, ultimately given all these, the uniquely defines the status of the system. Then these are called state variables. So, the state variables are Okay. Oh no, minimum number. The minimum number of minimum number of variables that uniquely define the dynamical status of a system. In general, in a mechanical system, what are these? How do you define them? We essentially define the different mass points, their positions and their momenta. Similarly, in electrical circuits, we locate the storage elements. Storage elements are the inductance and the capacitance, and the current through the inductances and the voltage across the capacitances, they uniquely define the state variables. In certain situations, the number of state variables may be less than the number of inductances and capacitance in a system. However, for this course, for the purpose of this particular course, we will not go into those issues. But essentially, just remember that this is the definition of state variable. So, in trying to understand any dynamical system, what we do is we write the equations, state variable equations as they are called. What does it mean? We write equations like this in terms of the state variables. So, in that case, x will no longer remain a number, x will become a vector, which means if say I have 3 variables in a system, I will write dx dt is equal to something, dy dt is equal to something else, dz dt is equal to again something else. So, this will be one function of x, y, z, another function of x, y, z, and a third function of x, y, and z. Given this, the differential equations are completely defined. Okay. And then you have also learned how to solve differential equations. Have you? More or less, right? At least you know how to solve a class of differential equations. Nobody can claim that you know how to solve differential equations, because nobody does know. Solving it means that either we are able to explicitly write down the solution, or we scratch our heads and say that no, we cannot do that, but given an initial condition, I can always tell where approximately the states will go by numerically solving it. That is how we finally do it mostly. But nevertheless, when we are doing that, what are we in essence doing? We are starting from an initial condition. That means here is my x, y, z at the initial time is equal to 0, and then it is evolving. Evolving in what? Now, the evolution you normally you have seen as something like this, right? You have seen as a waveform something like this, time versus a variable x. Similarly, there will be a waveform of say time versus the variable y. Similarly, there will be a waveform for the time versus the variable z. This is probably what you have already learned how to obtain. No? As I told you, at least for a class of systems. What kind of class of system you have learned? In all probability, you have learned how to do that in linear systems, where the right hand side are linear functions, is it not? But in general, as I told you, systems are nonlinear. In fact, all systems are nonlinear, and we will see what linear systems mean in the context of the general idea of nonlinear system. We will see that, but in essence we have this and we can obtain this. So, what are we exactly doing? in order to understand that, it is necessary for us to understand or grasp the idea of what is known as the state space. In this, what we do is, here we have the x, y, z. One of them could be a voltage across a capacitor, another one could be a voltage, a current through an inductor. If it is an electromechanical system, the third one could be even the momentum of a, say, a machine or something like that. So, in general, these are those state variables. In mechanical system, these are related to the positions and the momenta of the mass points. In electrical system, these are related to the capacitor voltages and inductor currents, and in electromechanical systems, it could be jumble of all these. So, notice that the moment we have written it in this form, we can, for all practical purposes, set aside the actual system description, forget whether something we are talking about is a voltage or a position, current or a momentum. We can forget about that, because we have written down the equations and we can go ahead with that, right. Maybe at a later stage, when you have understood it, we will have to translate it back in terms of what happens in the actual system, but presently we will assume that we have abstracted the system, and then we are not able to see the distinction between the x and the y and z. They are on the same pedestal, right. They have the same value for us in the differential equations. And then what we do is, we say that let there be a space where the x, y, z are the coordinates. It is quite unlike the space we live in, because it is in the space in which we live, x, y, z are the spatial coordinates. There is also a time coordinate t, but here we are not talking about that. Here we are talking about the voltage being a coordinate, the current being a coordinate, the momentum being a coordinate. That way we are representing it. So, that then, assuming it is a 2D system, then x and y are the state variables, and such a space is called a state space. Clear? Now, in that background, then the differential equations give a meaning. What do the differential equations say? It says that if the x, y, and z have a specific initial condition, say this. Here I am talking about the x, y space, but nevertheless it could be x, y, z space. An initial condition. Given that initial condition, if we solve these equations, we get some kind of a evolution in this space, right. So, the differential equations essentially tell how the state point is going to evolve in time in the state space. So, from now onwards, all our views will be directed to what happens in the state space, and we will try to understand visually in terms of visual impression. See, these are not things that we really see before our eyes, but in mind's imagination, at the end of the day, after you complete this course, you should be able to visualize, yes, it is happening like that. See, if you see a differential equation, okay. So, you have a set of differential equations telling you how the state evolves. At every point, the state is evolving depending on the set of differential equations, starting from an initial condition. That is the setting. Now, let us see how far this idea, how high this idea takes us till, in the language of Subramanian Chandrasekhar, till the sun melts the wax on our wings. He ended a chapter in his book with this. Let us see how far this takes us till the sun melts the wax in our wings. So, you have this. By the way, starting from here, how do we know where to go next? For example, at this point, somehow this point knows that it has to go in this direction. Next, how does it know? It knows from the differential equation, really, because here means a particular value of x, y and z, and if you substitute this value of x, y and z here in the right hand side, you get numbers, right? You get numbers here. So this equation tells that in the next instant it will move so much in x direction, so much in the y direction and so much in the z direction, and that together will define this vector. Okay. If the state point were here instead, same thing applies. You would have been able to calculate again by substituting the locations particular numbers here. You would have been able to calculate what is dx dt, dy dt and dz dt. Clear? Which means that irrespective of where I am, the set of differential equations tell where I should go. Which means that if I am here, the set of differential equations define an arrow. If I am here, the set of differential equations define an arrow. If I am here, the set of differential equations define an arrow. At every point in the state space, the differential equations define an arrow, right? So after you have written down the set of differential equations for any system, what I have essentially defined is, in the state space you have defined arrows at every location. If I am here, I know where to go. If I am here, I know where to go. As from here I start, I go on. When I reach here, still I know where to go. As it goes on, still this fellow knows where to go, and so it goes on traversing the trajectory. Clear? So essentially, the state space is completely defined in terms of the differential equations when you have defined the arrows at every point. Clear? This means that the differential equations define arrows at every point, and notice that the state evolves along the arrows, as if something is flowing and you put a drop on the in the flow, it flows along, right? The solution of differential equation is something like that. There is a stream and a leaf drops in it and it flows along with the rest of the flow. It flows exactly like that. So that is why a set of differential equation is also called a flow. In literature you will find this word flow. You will see sentences like, let us define a flow. What is a flow? It is just nothing but a set of differential equations. It defines a flow. And when a set of differential equations are given, it defines a vector at every point in the state space. That is why it is also called a vector field. Let us see how far this idea takes us till the sun melts our wings. So far, the kind of impression that you had was that you are able to solve a certain kind of differential equations, mainly linear differential equations. You are able to distinguish apart the particular integrals and all the other things, which means that given a starting point, given an initial condition, you are able to traverse for a certain specific set of differential equations. You cannot do it for everything. You have learned in the numerical analysis courses how to solve these differential equations numerically. Have you not? You have learned, most of you have learned. There also you have learned how to start from initial condition and then traverse the trajectory. But if I ask you, what all can this system do? What are the different types of dynamics possible for a system? Can you see? No. Then what will have to do? Start from all possible initial conditions and go on computing. Or if it is a solvable differential equation, then do you imagine how long will it take for you to tell what are the different types of dynamics possible for a system? You will have to solve it for every given initial condition, which means in the solutions you will have to calculate the C1, C2, all that for every single initial condition, and then you will scratch your head and give up. But the moment the state space and the vector field is pictorially in front of your eyes, you know what can happen. And now we will try to do that. For that purpose, let us start with one example system. Let us take this example, and this system. As we go on with this system, we will try to understand a few other concepts. Now, given this system, can you draw the vector field? You will be at a loss how to, right? So, start at the point that is simplest. What are the simplest? No, it may not be 0 0. See, you have to ask what in which positions in the state space does the left hand side vanish. Left hand side means x dot and y dot. X dot and y dot vanishing means if it is there, it remains there. These are equilibrium points. So, how to locate the equilibrium points? So, let us write where x dot equal to 0. For this system, can you obtain? Well, this fellow says x dot equal to 0 means y equal to 0. Now, y is equal to 0 if you put here, you get a quadratic equation. You need to solve it and then obtain the possible values of x for which it will be 0. And so there is only one equilibrium point. Yes, yeah. If you multiply by y, it is 0. Sorry, it does not get a quadratic here. So here in this case, x is equal to 0, y is equal to 0 is a solution. Now, therefore, we have the state x y state in which x equal to 0, y is equal to 0 is a equilibrium point. The next is, what we do next is, we take a magnifying glass and go very close to this equilibrium point and look at it. What is the structure of the state space or the vector field around it? That is the easiest to know, because as you zoom closer and closer, the nonlinearity in the system will slowly vanish. It is like you have got a curve, and as you zoom closer and closer, it becomes more and more like a straight line. So, as you zoom closer and closer, it will more and more lose its nonlinear character, and you will look at the linear neighborhood of this point. Okay. So, we are essentially zooming into this region. As you zoom, if you are looking at the linear neighborhood of that, the way when you are looking very close to this, if this is your y and this is your x, then what are you looking at this point? How do you represent the local linear representation? By dy dx, right? When you are zooming into a two-dimensional system and trying to to understand the location, you still have a 2D equation, right. You should still have something like this, x dot is equal to something which is a linear combination of x and y. So, something x plus something y, y dot is equal to again something x plus again something y, then it becomes a linear equation. What are these somethings? Probably you have learned that. How to obtain these somethings from this linear nonlinear differential equation? This has a name, the Jacobian matrix. This is the name, the Jacobian matrix. So, the Jacobian matrix is essentially nothing but, if you are zooming closer and closer to the equilibrium point, you get a local linear representation, and that local linear representation in the neighborhood of any point is given by the Jacobian matrix. So, what is the Jacobian matrix? The Jacobian matrix is then we will represent everything in terms of the deviation from the equilibrium point. In this case, it so happened that the equilibrium point is at the origin, but in other system it might not be so. So, in general we will write the deviation from the equilibrium point as delta x delta y, and then this will be given as so this is the Jacobian matrix. This is times this is delta x dot delta y dot. So, what have we done? In obtaining this, we have said that now let us say that the deviation from this equilibrium point, how does that vary? So, we have said that delta x, the deviation from the equilibrium point in the x direction varies as this, delta y varies as that. Can you obtain this for this system? Quickly obtain that. So, we will say this is f1 of xy and this is f2 of xy. So, the derivative of f1 with respect to x is 0, derivative of f1 with respect to y is 1 because it is only y, derivative of f2 with respect to x is minus twice xy minus 1. So, let us write it. This will become 0 1 minus twice xy minus 1, and here it is 1 minus x square. Well, you might say that here also I have something that is containing all these things. No, because you are trying to evaluate it where? At equilibrium point where x and y are 0. So, substitute these values and then that takes the form 0 1 minus 1 1. Then you would say that now in the neighborhood of this my differential equations are. So, this is the whole state space, here is my equilibrium point, I am now zooming into this part, and here the equilibrium the equations are x dot is, where are they, y, and y dot is minus x plus right. This is the method of local linearization. So, the Jacobian matrix is essentially a tool to obtain the local linearization, and then when we look at this equilibrium point and the behavior around it, it is sufficient to study this differential equation. Now, those of you who have gone through the course of control theory and courses like that in different departments, they go by different names, but nevertheless some course related to that, they will realize that in the whole of control theory studies, we essentially look at only this. We always take a magnifying glass and zoom close and close and close and say that I am happy, I have got a linear equation. And then what do we do? We say that now if we make a system work at that equilibrium point, I will make the tacit assumption that the deviations from the equilibrium point will never be sufficiently large, so that it goes beyond the range where this local linear approximation is valid, and then we work throughout our life with these equations. We normally forget that we actually started with a set of equations like this, but then it may actually so happen that in running in a particular system, it may really go beyond that because of either some kind of a failure or some kind of a overloading or some kind of a parameter perturbation that you really did not foresee. Of course, that also takes into account the possibility that you might actually want to use the rest of the system. You might actually not want the linear behavior to be used. I will come to where these are useful. But then here we are, we have a set of linear differential equations given by this. Now we can solve it, right? Can we all solve it? Can we all solve this? How will you solve? How will you solve this set of differential equations? Solve. Go ahead and solve on your copy. If you say that you can solve, I will demand that you do solve. Okay, to briefly recall the essential method of solving differential equations. It says this is a two-dimensional set of differential equations. Suppose you do not know how to solve a 2D system of differential equations, but then you are born with the knowledge of how to solve a one-dimensional differential equation, right? Probably when you came out of school, you came out with that knowledge, how to solve a one-dimensional differential equation. Say can you solve? Most of you can. So, the one-dimensional differential equation solution, as you know, is a exponential function. So, we know that. In case of 2D, the essential method of solving it is that we try to identify. Okay, there is a theorem that says that if I can locate any solution, just locate, if in a 2D system, just locate any possible two solutions, then any other solution is a linear combination of these solutions. Okay, we will not attempt to prove that theorem, because I will assume that you have come across that in your differential equation courses, but essentially everything builds on that theorem, which says that if I can locate any two solutions, then any possible solution starting from any initial condition is nothing but a linear combination of that. If it is a 3D set of equations, I need to identify three solutions, and so on and so forth. So, let us work initially with 2D. So, the mathematicians will say, what is the simplest way of identifying a solution in such a system? Now, the logic is as follows, that if you probably that you have come across in the matrix theory. Here you have a matrix, you can write it as a matrix 0 1 minus 1 1 x y, clear. So, if I write it in a compact form, I will write x dot is equal to a x, where x is a vector, x dot is also a vector. If I say it verbally, I will say a when operated on x gives me x dot. What the hell is a? An operator. An operator operating on the vector x, say a vector x, it is operating on the vector x giving me another vector x dot. Okay. In general, the vector on which it operates and the vector that you get, these are different in magnitude as well as direction. But then you have learned in your math courses that there exist in 2D system two directions, such that if the initial vector is along that direction, the x dot, the resultant vector, is also in the same direction. These are called the eigen directions. Okay, and any vector along the eigen direction is eigenvector, and therefore, in the eigen direction, suppose this is an eigen direction, and you take the x vector along that, and you get the x dot vector like this. That means it has been multiplied by a factor to get x dot by a scalar, right. The x has been multiplied by a number to get x dot. What is that number called? The eigenvalue, right. So, the mathematician would say in solving this, okay, let us see, if I can start with an initial condition on this line, then I know that the resultant x dot will be along the same line, and therefore, whatever it does, its evolution throughout will remain constant to this line. That is a one dimensional equation. Then I know how to solve it. I can write down this solution. Again, I can identify another direction, eigen direction like this. If I take an initial condition along that, I can again write down a first order equation. Solution I can write. So, the final solution is nothing but the combination, linear combination of this and that. Okay, that is the essential way of solving differential equations. Have you learned this? Na? Probably you have all gone through, or if not visibly, you are in your mind scratching your heads. What is it? Are you scratching or are you not scratching? Okay, at the end of the day, I will see how many hairs fall off. I assume that you know. By the way, if you don't, it is safe for you to tell I don't, and therefore, please cover it, sir. Else I will assume that you know, and I will go ahead. I will go ahead. You have forgotten differential equations? No, see, there are certain things that you learn. My teacher used to say that supposing you meet an accident, you are about to be carried to the hospital and you have to tell something, then you should be able to tell your name, your father's name, and the differential equation. So it should be ingrained in your knowledge to such an extent that you should be able to say in that status, okay, I know it is by minus 80. So what should I do? Forgotten? Why are you murmuring that you have forgotten? If you have forgotten, just say it. What do I do? If I want to cover the whole thing, it will take a reasonably long time. So what I'll do is I'll advise you to simply see the video lectures of my other course, Dynamics of Physical Systems. They are available on the net. There are set of lectures on the solution of linear differential equations. Just read those, just see those, because otherwise I'll have to traverse the whole thing that I traverse in the other course, which are available in the video lectures. The course title is Dynamics of Physical Systems. But what I really need to cover is that what you essentially do is to obtain the differential equations, the eigenvalues and eigenvectors of this, by writing it as what? By writing, see, the logic is that here I start from a vector, and what I get is also along the same line. So A operated on x is a we essentially do this, and then we say a minus lambda I x is equal to 0. So this fellow's determinant should be 0. That we obtain a quadratic equation for a two-dimensional system. Solving it, we get two eigenvalues. Now the eigenvalues therefore are the solution of a quadratic equation in case of 2D system. In a 3D system it would be a cubic equation you have to solve. But then a quadratic equations may have both a real solution as well as imaginary solution. Okay. A real solution can be positive or negative. For the purpose of this course, it will be necessary. This I cannot allow you to simply read from the other things. This is something again you will be able to utter just before you die. It should be so closely ingrained in your psychology. So there are various possibilities. In general, we can say if we have this as the complex plane, the real and imaginary, then the eigenvalues can be on the positive real line, can be on the negative real line, can be like this, can be like that, and each case you should at least know, you should at least be able to tell what will be the system's behavior like. Even if you say that I have forgotten how to solve differential equations, fine, I accept it, no problem, you can always learn it. But this is a concept. Here is something that is a concept, that if the eigenvalues are such, the behavior will be so. That you should know by heart. Now do remember that. What if the eigenvalues are, say, here, the two eigenvalues both real and negative? Exponential decay. The logic, simply try to understand the logic, because that is what will lead your thoughts. So don't just remember. When I say something, don't remember, try to understand the logic, and that's enough. The actual algebra you can all do. So in a system, if this is your x and y, and say this is one eigen direction and this is another eigen direction, and along this eigen direction there is one eigenvalue at -1, there is another eigenvalue at -3. So suppose along this we have got a eigenvalue at -1, and along this you have got an eigenvalue at -3. What does it mean? It means that if the x is along that, x dot will be -1 times this. Minus means it will be opposite direction. So x dot will be along this direction, So x is this much, x dot in the opposite direction, what does it mean? It will move with time in this direction. Okay. So it will always remain along this eigenvector and it will decay, its distance from the equilibrium point will die down, and the more it comes closer, the slower the rate of dying down, because x times -1 is the rate. When it becomes very close, the rate also becomes very slow. So naturally it has to be exponential, right? You don't really have to memorize that it has to be exponential, sir. You don't have to memorize. It's quite logical that it can be nothing but exponential. Clear? Similarly, if it is here along this line, it will die down. It will die down faster because -3, right? So it will die down faster along this direction. Now, if you have got the initial condition somewhere else, then when I say that the resulting solution is a linear combination of this solution and that solution, what does it mean? It means that you can drop a component, a projection of this point on this and on that. So this vector can be broken up into a vector along this, another vector along that. This vector will die down as e to the power -1t, and this vector will die down at a rate e to the power -3t. As a result, this will finally come closer and closer to the equilibrium point. How? Can you figure out how? Will it come like this? No, it cannot come like that. It will die down faster in that direction, and therefore it will come like this. Right? If it is here, again you drop projections and you will see that it goes like this. If it is here, it goes like this. If it is here, it goes like this. So you see, you essentially get a evolution like this. Does do these curved arrows make sense? It says that if it is here, it will go like this. If it is here, it will go like that, which means that it will converge first onto this eigenvector, and then along that eigenvector it will approach the equilibrium point. Right? It will not just decay just any which way. It will decay in a specific way. Is that understandable? Okay. So you see, you can then draw a picture of the whole state space. The moment you look at this state space, you know all that it can do. Okay, or you know what? So this is the diagram of the vector field. You can yourself draw. You don't really need to point at every place and then you draw the arrow. That's not necessary. You know that starting from such an initial condition, it will go like that. Starting from another initial condition, if you start from some representative initial conditions and if you draw the lines along which it will go, it gives an idea. So if both the equilibrium points, both the eigenvalues are negative and real, it will go like this. If both the eigenvalues are real and positive, it will be just the opposite. It will be similar, only the direction of the arrows will be opposite. So initial condition, if an initial condition starts very close to the equilibrium point, it will diverge away. Notice the logic. You have got this direction as the eigen direction. Start from this initial condition. If this is x, this is x vector. Where is the x dot vector? No, not opposite. If it is real and positive, then it will be in the same direction, so that it will go further along that. outwards. As it goes here, it again has a vector pointing outwards, so on and so forth. So similarly it will go out. So it will go out. Therefore its vector field picture will look similar only with the arrows pointing in the outward directions for lambda plus b positive. If the eigenvalues are one positive, another negative, if one eigenvalue is positive, another negative, wait, in that case let us draw. You have this state space picture x, y, and suppose this is one direction and this is another direction, and here I have the eigenvalue plus 1 and here it is minus 2. क्या होगा? What happened? What will happen? Wait. If there is any initial condition exactly on this point, it will diverge. If there is any initial condition exactly on this line, it will converge. So this is the converging direction and this is the diverging direction. If there is any initial condition elsewhere, say here, what will happen? How will the orbit be like? Again, drop a projection on this and drop a projection on that. Your argument should be that this particular projection, it should increase, this length should decrease, and therefore it should evolve as this, right? And if I draw the others, say here it will go like this, from here it will go like that, from here it will go like that, from here it will go like that. So there exists a very small region in the state space from which it converges. Everywhere else it will ultimately diverge, and the set of initial conditions on which, if it is placed, if the initial condition is placed, it will converge. How small is the space of initial conditions? Of measure 0. Out of this 2D space, it is just a line. Therefore, for all practical purposes, we will say the system is unstable. We will say the system is. This is similar to the view of a saddle, right? If you have a saddle, then if you release a ball here, it goes this way, converges, and if you release a ball here, it goes this way, diverges. So it has a structure like a saddle. That's why this kind of equilibrium point is called a saddle. Fine. Okay, let's stop here and we'll continue with in the next class. Before that, those of you who are scratching your head saying that I have forgotten, sir, please revisit the dynamics of physical systems classes where I was dealing with the solution of linear differential equations.